Let's look at the first example. In the first example, we're going to find a VO in the network using source transformation. VO is over here, and by looking at the left-hand side, it does have a current source, and the right-hand side it has a voltage source, and eventually we want to convert the two sides to be a very simplified circuit so that we can solve for VO. That is the idea. So I'm going to simplify this slowly, step by step. Let's see what we have here. On the left-hand side, this is a current source. We have this current source. We have one branch in parallel with this current source, and a second branch in parallel with this current source. It means these two branches are in parallel. So it means that I can simplify this part of the circuit to be a voltage source with a run resistor in parallel with that. So this is the first part of my circuit. So I'm going to simplify this part. I'm going to transform part 1. And we're going to simplify that to be one voltage source in series with one resistor. So we want to simplify the left-hand side to be this part. So what is the equivalent resistance? That will be these two branches in parallel, right? So that is 2 plus 4 in parallel with 6. So let's call it R1. 2 plus 4 in parallel with 12. So that is 4 kilo ohm. And we can find the equivalent voltage source, let's call it a V1. And the voltage source will be equal to this current times the resistance, right? So the resistance is 4K, we already did that. And the current is 2 milliamp. 2 milliamp times 4K, so that will give us 8 volts. So we simplify the part of the circuit. For the second part of the circuit, let's call this part of the circuit part 2. Since the part 2 that it has a voltage source, we're going to convert it to be a current source in parallel with the one resistor. And pay attention to the direction of the current source. Since the voltage source has a positive reference polarity on the top, then the current should flow upward. And it will in parallel with the one resistor. And we know the resistance for this resistor R2 will be equal to the same resistor in the network, which is 4 kilo ohm. R2 is equal to 4 milliamp. And the current source I2 is equal to the voltage 12 divided by 4. That is equal to 3 milliamp. Then further we can simplify this part, include the other 12K resistor. So let's call that part of the circuit to be part 3. And part 3 we'll need to use, this is part 2. This resistor R2 will be in parallel with this 12K resistor. So 12K in parallel with 4K. We're going to convert this current source to be the voltage source. And what will be the resistance in the voltage source for this resistor over there? Because we have a 4 in parallel with the 12. So resistor R3 is equal to 4 in parallel with 12. That will be 3K. And how about this voltage source V2? So V2 will be equal to I2 times this new resistor, right?
So it'll be 9, yeah.
So V2 will be equal to I2 times R3. That is 9 volts. So let's check the direction. So this reference goes upward, this current voltage source, the upside should be the reference positive. So now we complete all these 3 parts. We're going to bring them together to find the equivalent network. So we're going to replace this whole thing and this whole thing on this side. The left-hand side will be this, right? Because we simplify this part 1. And the right-hand side will be this. So we put this back into the circuit. Now we find the circuit is very simplified, right? We have 2 sources, and we're going to find the voltage drop on this 3K resistor. The voltage drop from the left to the right, that is 8 minus 9. So we can find the voltage VO. We can find VO by using the voltage division. This is 3K. The total resistance is 3K plus R1 plus R2 times the voltage drop. The voltage drop is equal to V1 minus V2. So V1 minus V2 is equal to -1, and R1 is equal to 4. R2, no, this is not R2, R3. R3 is equal to 3. So the final answer should be -0.3 volt. Let's look at the second example. use Thevenin's theorem to find a VO in the network. So VO is over here. So the idea to use Thevenin's theorem to solve this problem is to take this off, and we look at the equivalent circuit to the rest. Take this off, and we're going to find the equivalent to this part of the circuit. Find an equivalent to the following part of the circuit. After we find the equivalent circuit, we'll bring the resistor back so that we can solve the problem. How do we find an equivalent to this circuit? We talk about 3 different cases, and this is the first case where we only have independent power sources, right? So first step is to find a VOC. Step 1.1, find a VOC. VOC represents open circuit voltage. We want to give it a reference polarity. Let's call the reference side to be positive and the right hand side to be negative. So this is the reference polarity that we give. You can give it in the other direction, but you just need to make sure the way that you define it should be consistent with the way that how you draw the Thevenin's equivalent circuit. In this problem, we can find VOC by using the definition. VOC is the voltage difference between this node and that node. We can use the voltage drop on this 6 kilo ohm resistor plus the voltage drop on this 2 kilo ohm resistor. The voltage drop on this 6K resistor, that is we can find that by using the voltage division, right? So that is 6K over 6K plus 3K times the total voltage drop from this node to that node, which is 12 volts. The voltage drop on this 2K resistor from the bottom node to the top node, that can be found by using Ohm's law, which is the current 2 times the resistance 2. So plus 2 times 2. So that will give us the voltage drop VOC. That is 12 volts. Next, we're going to find a RTH. So to find out RTH, we need to set all the power sources to be 0 to look at what is the internal resistor network. So how do we set the 2 milliamp to be 0? We just need to open it. And how do we make the voltage source to be 0? We replace that by a wire. This is our equivalent resistor network. So look at the connection. One resistor in series with the rest. So these 2 resistors are in parallel. So that is how we find equivalent resistance. 2 in series with a 3 and a 6 in parallel. That is 4 kilo ohm. Now we find both VOC and RTH. It means that we find it's a Thevenin equivalent. The Thevenin's equivalent have a form like this. It's composed of one voltage source, and this voltage source is the same as a VOC. And the resistor have a value of RTH. So this is the Thevenin's equivalent. The next step, we're going to connect the circuit back to this Thevenin's equivalent. Then we'll be able to solve the problem. Let me just call this step 2 then. We draw the Thevenin's equivalent circuit. So I'm going to add this 4 kilo ohm back to the circuit. How do I know the reference direction? Should I connect this to the circuit network, or I should do it like this? So this is something that you need to pay attention. Look, this is how we define a VOC. The reference polarity that we select for VOC is the positive on the left-hand side. So if we look at the Thevenin equivalents, so this top side should be positive for Thevenin equivalent, right? That is what we draw here. We draw the top as a positive. So it means that this top side is positive. And look, we define a VOC in the same reference polarity as a VO. So it means this reference positive direction and positive side should be the same as that positive side. So this top is our positive side for Thevenin equivalent circuit. It means the top side should also be the positive side for my VO. So every semester there are students making mistakes here. Next step to find a VO, this is pretty straightforward. It's the same thing as how we find a VOC. We will use the voltage division to find a VO. VO is equal to 4 over 4 plus RTH times the total voltage VOC. You can also call it a VTH. That's the same. So VOC we found is equal to 12. Now it's half of that, it becomes 6 volts. So this is how we solve this problem by using Thevenin's equivalent. The next example will be about a second special case. For a circuit with only dependent sources, in this problem, we're going to find a Thevenin's equivalent of the network at a terminal AB. And in this problem, it doesn't have any independent sources. It means the circuit cannot self-excite. So it also implies that a VOC is equal to 0. So step 1, find a VOC. Since this circuit has only dependent sources, VOC is equal to 0. And if we find an ISC, we're going to find our ISC is also equal to 0 because it doesn't have an internal excitation. So we're going to be able to use that general method to find an ISC, then find an RTH. So in this problem, we need to add an external power supply so that we can calculate RTH. There are two different ways to do it. You can add a voltage source to calculate the current, or you add a current source to calculate the voltage. Assume we're going to add a voltage source and then find the current I. And this voltage source have a voltage of 1 volt. And this is not a VOC, remember. So let's call this a voltage Vs that is equal to 1 volt. What is the current direction? Is it to the left or to the right? Here we need to
the left.
Define it to the left. Eventually we want to find the resistance of the network. If we add a voltage source like that, the current should be defined to the left. We call this current I. Let's see how we find the current I. We can select either nodal analysis or loop analysis to solve this problem, right? If we select nodal analysis, if we select the reference node to be here, and the nodal voltage here, that is 1 volt, right? If we make full use of Vx, we know the voltage here, that is 2Vx, because this is 1K, and this voltage is 2Vx. If you can see it. If you cannot, then we'll just call this node have a nodal voltage of V1. So just assume that we cannot see that relationship right away. So in that case, I'm going to define this as V1. So we define all the nodal voltages. The next step is to write a nodal equation. Which node are you going to pick to write a nodal equation?
V1.
Good choice. So we count all the current leaving the node as up to 0. The current leaving this node, that is V1 divided by the resistance in that branch, so that is 2. The current leaving this node in this branch, that is negative Vx. The current leaving this node from this branch, that is V1 minus 1 divided by 2. There are only 3 branches connected to this node, so this will add up to 0. So this is the first equation. And the second equation comes from the controlling variable, which is Vx. We need to find a relationship between Vx and all the other nodal voltages we defined. We only define one nodal voltage, which is V1. What's the relationship between Vx and V1? So we already mentioned that, right? Vx is equal to half V1. Now we have two equations with two unknowns. We can solve it. We find V1 is equal to 1, and Vx is equal to 0.5 volts. So we were trying to solve current I. The current goes into this node will be equal to the current leaving the node, right? We can find it that way. So the current leaving this node is equal to 1 volt divided by 1 kilo ohm, 1 over 1, plus 1 volt minus V1 divided by 2K. And we found V1 is equal to 1 volt. We know that I is equal to 1 milliamp. So after we find I, we'll be able to calculate the resistance. Step 3, find RTH. We can find RTH by using Ohm's law. We add the voltage of 1 volt, and we see current 1 milliamp. So we know the resistance is 1 kilo ohm. Then we can draw the conclusion. This problem asks for the Thevenin equivalent circuit with VOC is equal to 0 and RTH is equal to 1 kilo ohm. So let's look at this problem. So this problem looks much more complex compared to the previous one, right? And by looking at this problem, we see independent sources At the same time, we see dependent sources. So it implies that we can only use the general method to solve this problem. The idea of using Thevenin's equivalent theorem to solve this problem is to find the equivalent to the rest of the network, except this resistor 1K. So how do we find a VOC here? I cannot see the answer right away. Looks like I need to use either nodal analysis or loop analysis, right? Because it has two current source, so I will assume that it's a little bit easier to use a loop analysis. Let me define my current. Let's call this current I1, and the second current will be defined here. Let's call this I2, and the third mesh current, let's define it to be here. Let's call this I3. What is I1?
1 million.
1 milliamp. How about I2?
4 million.
4?
-4.
-4.
-4 milliamp. And how about I3? 2Vx, right?
2Vx.
It's 2Vx. So now we have this 3 current and we have one additional unknown, which is Vx. We need to find this control variable in terms of I1, I2, and I3. Where is the Vx? Vx is defined over there. What is Vx in this problem? Tell me your answer in chat. So think about it. Okay, send your answer on chat. I got some answer and most of you said 0. Yeah, here is correct. It's 0. There's no current. It means there's no voltage drop. So Vx is equal to 0. So if Vx is equal to 0 and I3 is equal to 0 as well, we are looking for VOC. Let's see how we can find a VOC. We're going to find a VOC by using Ohm's law and the definition. The VOC is the voltage drop from here to there. So the first voltage drop on this resistor, that is Vx, is equal to 0. We already know that. The voltage drop on this resistor is 1 kilo ohm times the current negative I1, because we are looking for the voltage from this node to that node. And this 2K is the same, right? So we just put them together. 1 plus 2 times negative I1, so that is the voltage drop from here to here. Plus the voltage drop on this 1K resistor. The voltage drop on this 1K resistor is equal to I1 times I3 minus I1. And the voltage drop on this 1K resistor, that is 1K times the current flow from the left to the right, which is I2. That gives us negative 8 volts. Second step, we need to find the short circuit current, ISC. How do you find ISC? Which method do you want to use to find this current in this branch? So you will do loop analysis. We know the current here, we know the current here, cannot, but at the same time there is a shared current source. It means that we need to either use the general loop method or super mesh method to solve the relationship between these two, right? Looks like it's not easy. And if we do nodal analysis, if we select one node as reference node, basically level the nodal voltages, we have 4 different nodal voltages. So the complexity is pretty similar, right? So let's continue using loop analysis then. So we define this current I1, let's call this current I2, and this is I3. So it's better to give them different naming for the same problem to avoid any confusion. So let's call this I4, 5, 6, 7. The first equation that we have is about these two meshes. These two meshes give us one constraint, which is I4 minus I5 is equal to 1 milliamp. And the current in this loop, I7, is equal to negative 4. And the current in this mesh, I6, is equal to 2Vx. At the same time, we are short of one equation, so let's use the general loop method to find additional equation from this super mesh. So super mesh is obtained by open this shared current source. It open up another mesh, so that we'll define that as a super mesh. So this is our super mesh. We'll write the equation about this super mesh by using KVL. So the first voltage drop on this 2K and 1K, 2 plus 1 times the current I4. The voltage drop on this 1K resistor, that is 1K times current I5. The voltage drop on this 1K resistor is 1K times I5 minus I7. And the voltage drop on this 1K resistor is 1K times I4 minus I6. So we add all the voltage drop for this whole super mesh. We have 4 different equations, but we have 5 unknowns because there is one more control variable. So the last equation is about this control variable. We're going to find Vx by using Ohm's law. Vx is the voltage drop on this 1K resistor, which is equal to 1 times negative I5. Alright, now we got all the equations. Alright, let's solve this. I4 is equal to 0, and I5, let me know if you get a different answer. I find I5 is equal to negative 1 milliamp, and I6 is equal to 2 milliamp. I7 is equal to negative 4 milliamp. And over here, Vx is equal to 1 volt. ISC is the same as I5. So we get ISC is equal to negative 1 milliamp. So step 3, the Thevenin's equivalent circuit will be of that form, and the VOC is equal to negative 8 volt. And RTH is equal to VOC divided by ISC. Negative 8 over negative 1, so that is 8 kilo ohm. So step 4, we're going to put this circuit together and we'll find a VO. Alright, so I made a little bit of space. So I need to add the resistor back into the circuit so that I can find a VO. Step 4, find the conclusion. We find a VO by using the voltage division, which is the resistor 1 over total resistance is 1 plus RTH. RTH is 8 times the voltage. The voltage VOC is equal to negative 8. So we find the answer to be negative 8 over 9 volt. So the next problem is a little bit easier compared to the previous problem, but it has an additional step where it requires you to use the maximum power transfer theorem to find RL in the circuit. We know that if we can find the equivalent, Thevenin's equivalent for the rest of the network without this load resistor RL, we will find it to be one resistor. Let me draw that. If we do that, if we find a Thevenin equivalent to the part of the circuit, we will eventually get something like this. And this is the resistor RL. From maximum power transfer theorem, RL has to be equal to RTH so that RL will have a maximum power. So now the problem becomes to find a Thevenin equivalent, the same thing. So I'm going to let you to work on the problem, then pair with mine. So first step, I'm going to find a VOC. So VOC is found for this circuit without this resistor RL. In this problem, I might consider using nodal analysis. So if I use a nodal analysis, let's say I select this node as reference node, use nodal analysis. So let's call this node, give it a name V1. So this node have a nodal voltage of 100. And this node have a nodal voltage here, which is 20. And since this is 100, I know the nodal voltage here, that is 100 plus 4Vx. So now I get all the nodal voltages. I'm going to write a nodal equation about this node V1. V1 minus 20 divided by the 4 ohm, that is the current in that branch. The current in this branch. The current in this branch is V1 minus 100 divided by 4. The current in this branch is V1 minus 100 plus 4Vx divided by 4. That is equal to 0. So this is the KCL equation. And since we have one dependent variable, I need to find the relationship between Vx and the nodal voltages that I defined. Vx is here. So Vx is the voltage difference between V1 and 20. So Vx is equal to V1 minus 20. Now I have all my equations. I just need to solve them. Solve this equation that give us, let me see what that is. V1 is equal to negative 120. And now I can find a VOC. VOC is the voltage here. I'm going to count the voltage drop on this 4 ohm resistor plus this Vx plus 20. So from the top we find a Vx already. Vx is equal to negative 140. So VOC is equal to 100 plus 4Vx minus V1 divided by 2. The voltage drop on this 4 ohm resistor plus V1 minus 290. My numbers are a little bit strange. Did you get the same answer? Next step, I'm going to find an ISC. Tyler said she got a negative 140 for V1.
Yes, I got for V1 negative 140 as well.
Let me do it again. So it's 100 V1 20. Okay, no problem. This is 100 plus 4Vx, no problem. So is V1 minus 20 divided by 4. V1 minus 100 divided by 4. This is V1 minus 100 plus 4Vx divided by 4. So the equation is correct. So let's see how we solved it. So Vx is equal to V1 minus 20. So that is also correct. So all the equations are correct. So let's see the answer. So this is 3Vx. Tell me your calculation. 3V1.
Doing it again, I got the same, the 140 and the 160, both negative though. That's what
Me too. I got those answers as well. Negative 140, negative 160.
That's why I was a little confused. Like the previous YouTube video, like I was like, okay.
It doesn't matter. So the answer doesn't matter. So pay attention to the equations. So the equations should be correct. Let me verify this to make sure that we have it solved correctly. I think we went over time already. So if you have other classes, feel free to leave to join other classes, and I'm just going to stay here to solve this problem. And after I finish solving this problem, I will go to the office hour. Yeah, even if you watch the previous year's YouTube video, if they have if they get a different number, so I want you to verify it. Okay. 3V1 minus 220. Minus 4Vx V1 minus 20. Negative V1 plus 80 is equal to 0. So V1 is equal to negative 140. Yes, you are correct. So V1 is a negative 140 and Vx is a negative 160. Okay, perfect. So now we find a VOC. VOC is what is VOC? Now the next step we're going to find ISC. ISC is a short circuit current. The current will flow from the top to the bottom. So we can do the same. We can use a nodal analysis to solve this problem. So I'm going to select this node as my reference node. I'm going to define the nodal voltages. Let's call this node V2, and this node will be the same 100, and this node will be the same 100 plus 4Vx. This is the reference node. So we can write a nodal equation about this node V2. We have V2 minus 100 divided by 4, the current in this branch. The current in this branch is the same V2 minus 20 divided by 4, and the current in this branch, that is V2 minus 0 divided by 4. So we get all these three different branches, so that is equal to 0. That is the equation at this node. So we can find a V2. V2 is equal to 40 volts. Vx is equal to V2 minus 20, so that is a 20 volts. So now we have enough to find ISC. We will be able to find IC by using KCL. The current goes into this node is equal to the current leaving the node. The current goes into this node is equal to V2 divided by 4 plus this 100 plus 4Vx divided by 4. So I get a ISC is equal to 55 amp. So after we get this, we can find a Thevenin equivalent. Thevenin equivalent will be something like this. VOC, we already have it. VOC is equal to negative 340. This is strange. RTH cannot be a negative number. Did I do anything wrong in calculating ISC? Yeah, V1 is equal to 260. And how about Vx? Vx is equal to V1 minus 20. That should be 240 volts, right? So VOC over here is 660. That makes sense. RTH will be VOC divided by 55, so that will give us 12 ohm. Last step, draw the conclusion. We know that RL has to be equal to RTH, so that the maximum power can be obtained, right? RL is equal to RTH is equal to 12 ohm, and under this condition, the maximum power P max, so half VOC squared over RL. So the maximum power is 9,075 watts.